often when interacting or using tensors, whether numerically or using them by hand while doing math, it gets a little tedious and a little difficult to track the indices that you're using or that you're contracting over. Depending on what kind of operation you want to do, you may want to permute indices, you might want to move them around or cast them to matrix form, and it gets a little bit tricky to follow what's going on. One kind of neat tool that you can use is called Einstein summation convention, which is a trick to kind of reduce the visual clutter and actually produce something that maybe a little bit is easier to track and to write down your equations with. Moreover, this is also available numerically, or you can use something similar to it numerically that can also simplify your life when writing code. This can be from machine learning examples, machine learning, just even tensor network techniques, or however you would like. There's many ways you can approach this, but there are some nice functions that are common, or some functionality that's common and used in other libraries and in other languages to do this. So one version is called an einsum, which is just a nifty little piece of code where you feed in indices and you ask for spitting out of indices, and then the matching of these indices will be done automatically for you. So today I'd actually like to build one in Aleph directly in our workshop, and kind of go through how one should think about it, what are some quick ways, and then see how we can potentially improve it. So first off, what is Einstein summation convention? So einsum stands for Einstein summation convention, and really it's just a notational trick developed in physics to help simplify expressions. So here on the right, you can see where I'm using a markdown preview of some files I have, and I rendered this typesetting, and you can see that I have the tensor. Let's make this a little bit bigger. I made this tensor tijln, and it's really from the contraction or the summing over the I, k, and m indices, which is also done in, which can be written like so, of u and v. But in practice, this is just really three sums that occur over I, k, and m, and I have these like tensors that have tons of indices. Now, this looks a bit difficult to follow, so we can establish like a little convention between you and I that can make things a little bit simpler. So first, we're going to drop the summation symbols. And if we do so, we need a way to kind of implicitly know what we're summing over. And we're going to say we're implying that a summation occurs when there are repeated indices, namely when you see the same index appear in both tensors. So for example, here what we can do is we can have the tensor tjln is equal to uijklm. Well, you could read it here. And every time you see an I present, regardless of where it appears, or wherever it appears, it's contracted over. So in this case, it's I, k, and m. It's the same as above. We just drop the sums. So you could just think of it as drop the sums. You see repeated indices. It's implied that it's summed over. So when you want to actually interact or operate with or perform this operation, you need to remember that you need to sum over these things. So this is great and all, but it gets a bit tricky when having to port this to the numerical context, so in programming. So it's certainly elegant, but it's not easy to convert from these expressions into code. So because the order of contractions may matter. So you want some level of control over, okay, which contraction is happening and how should it occur. Permuting indices mathematically is also really simple. You can just swap things and maybe write down a little object, but to actually perform the computation of the permutation, you kind of need to be also kind of with your wherewithal and to see where you actually need to apply permutation if needed to, especially when casting to matrices or tensors, because the ordering might matter. So a nice little trick, like I mentioned, is einsum. So what would an einsum look like? So suppose I'll just write some LaTeX here really quickly. Suppose I have some tensor CIK, and I'm actually going to perform the summation, or the contraction, I should say, like so. JK. In this case, because J is repeated both, it's summed over. So this is just matrix multiplication, right? So it would be nice if I could take something like, I could write a function that would do something like C1, and I could write einsum like this, and I could say maybe feed a string, let's say ij, jk, and I want to sum over the jth index, or I want to return to have, I want my final indices for C1 to be I and k. So here I have I and k. That's what I would like. And then I'll pass in A and B. But, you know, in some sense, what's nice about this is that I should be able to also do the same thing here, except maybe I don't want to return IK, maybe I want the transpose. so I would do ki. So these things would actually yield two different kinds of results. So einsum kind of helps you do this, where you don't need to worry about doing the transpose or hard code it. It just kind of knows where the indices are ordered, and it'll permute the tensor that you care about. So we need basically 3 to 4 things to do this. So what we need is first just a way to find the common indices in the two input strings. So I'm going to make a function. We're going to call this einsum. It's going to take in a string, and it's going to be called, we call this ins A, string ins B, and string ins C. So these are, I should call this a string and separate it, and then I'm just going to pass just A and B to be objects like so. Okay, so this is the syntax I want. I want to feed in the indices of A, indices of B, and then the desired output indices C. So first what we need to do is we need to parse the index, so the indices. So we need to know kind of what's repeated, what's not, and what are the common tensors, or the common indices to both tensors. So one way we can do this is the following. I'm actually just going to put this code in like so. Okay, and we're going to go through it together. So how does this work? Well, what we want is we want to make two lists. So dynamically, so this is a dynamic process, and this will kind of be the bottleneck for the operation. We're going to do this. We're going to create, we're going to loop over the strings of A, and then we're going to see, okay, does this letter appear in B? This is not the most efficient way to do this, but this is just certainly one way that you can do this. So we're going to look at the indices, and if they agree, so if we see the same letter appearing, we're going to add them to our dynamic lists of repeated indices. So now that we have that, all we need to do is just perform the contraction. So this is fairly simple. All we do is we'll have our result C, and we're going to just call the contract method. So in Aleph we have tensors. This is the API for, or the function signature for tensors. So what we do is we feed in A and B. We feed the dimensions of A that match to the corresponding dimensions in B. And we pass the two lists of these, and then it'll perform the contraction for you, and this is all the heavy lifting that's done. Now, however, we do need to wrap a couple things in together. So now that we've performed the contraction, so let me just say perform contraction. Here we'll say get repeated indices. Okay, so now what we need to do is we need to find the remaining indices. So right now we've summed over everything, but like I said, in our example, we need to find the indices that are left over, or those that are kind of not doing anything. And so again, this is not the fastest way to do this, but it is certainly a way to do it, is to then make another list of the remaining indices. Then we're going to loop over the initial indices. So strings can be used as can be index like lists in Aleph. And so what we're going to do is we're going to query the list, and we're going to ask, okay, where's the index at which A appears? If it is positive, it means that there is an index that corresponds to A. So i.e. there is this is present in dims A. If it's not present though, this should give a negative value, and so this condition will trigger, and it will add the indices that are not present in dims A into the remaining indices. And we do this both times because we have two tensors, so we need to see of the two tensors which ones are left over. This is fairly straightforward, but now that we've matched this, we need to perform one last thing, which is that basically the issue that we have now that we just need to resolve at the end is, so we've found the last indices, but they may appear in a different order. So this traverses the array of the list in a given order, but that might not be the desired output order. So you can add some guards here, but again, the fastest way to say it is just to you need to calculate the permutation of the indices. Like so. So again, we make another list, and what we're going to do is we're going to look at the output indices. We're going to start at 0. We're going to loop over them, and we're going to see what the position is of the remaining indices. So there should be a guard here for checking to make sure that the permutation does agree that, bug here. There needs to be a agreement between the contents of the list, so they need to be of the same size and the same elements, but at best shuffled with the output indices in C. So here we follow the same idea. We get the position of the remaining index, and so this will throw an error if this is negative. So there is a guard that should be added here, but just for brevity, I won't do this. So the remaining indices should be present in this list, so it'll just spit out the position at which it occurs. Then we're going to push back the this position to the permutation. So this constructs the permutation. It traverses it linearly and it checks, okay, where is it actually in the next one? And then you'll get a list of the shuffled indices. What we need to do here is we just need to, at the end, return C with transpose of the permutation. Okay. So there should also be a check for if the permutation is even doing anything. This might be the identity, and then this is a little bit costly, but this isn't designed to be performant. Just that how quick you can do all of this. So this should work in principle. So for example, now we built our function. So okay, we're just gonna make some random tensors. We're gonna do 2, 3, 4. It's complex. Let's do this as well. I'll call this B. We'll do 3, 4, and 5. Okay. So in this case, here are our indices. We only see that we match 3 and 4 and 4 and 4 here. So these are the first two indices of B, and these are the two later indices of A. So now if we want to do something, so in principle what this is doing is this is doing like AI JK times B JKL. And we're going to spit this out into something like so. And so if I do this, we'll do like so. We're going to do, we'll label them just like we did in the example. We'll do IJK, we'll do JKL, and we're going to spit this out into IL. And we're going to pass A and B. And then we're going to print the shape of the tensor to make sure that it agrees. So our prediction here is that since we're contracting, we're going to finish with I and L. I is the first index of A, and it's of dimension 2, and L is the last index of B, and so it should be of dimension 5. So this should be 2 by 5. So if I run this, should compile. I have an error. Okay, I have a typo remaining. Oh, let's not schedule a job here. Let's get this to run. Permutation, we are upset. Permutation, I cannot spell. And there we go. Oh, perfect. So we execute our code and we see that we get the size 2 by 5. Now let's do another one. Let's just do the reverse case, so to make sure our permutation is indeed working. And so what we're going to do is we're going to do IJK as well. We're going to do JKL again, but now we're going to have it do the transpose. So now it's going to be LI. And so if we pass this again, or I could, let's do C2, call this C1. And we're going to just do this here and go like so. And then perfect, it's 5 by 2. So it does it well. Now this is by any means, this is not like a full implementation of what like a general einsum can be. This is just a very simple example where we kind of wrap tensor contraction around this. But there's a couple things that you could kind of think about already, which is really, what are bottlenecks here? One that you can establish directly is that I'm double for looping over things. Maybe there's a better way to proceed. And there indeed probably is. Can we generalize? You can also generalize this einsum. So if you want to keep going, you could actually add logic between this. You can have a single string, so it doesn't need to be 3 different strings. Maybe it can be like 2 blocks of strings separated by some kind of delimiter, and then have another character that catches the output. You can also do that as well. And so one quick thing we can do is just ask Kai, be like, I want to make the einsum function faster, I believe the bottlenecks, if I can spell, bottlenecks are, is that not how you spell that? We'll find out. Bottleneck. There's no K. It's not like night. I believe the bottleneck is with the double for loops and other loops involving the index parsing. Next parsing. Look at the documentation and provide me with some recommendations. Recommendations to speed up the loops. So this is of course our feature with our native LLM integration, and so Kai, our AI, has access to here we go, it's just like this. And so it's giving kind of little suggestions, might compare some complexity, and it also kind of will give you kind of the summary at the end. It's the contract and transpose. And so you can see here, it gives you a couple options. So here, the first one, it's about eliminating inner loops, and it uses, let's see, so uses contains. So we can reduce one, so that would be a speed up, and other here as well. So this is what we would have here, which is actually quite nice. Use find first of, it's also very nice. So this will traverse the array, which is quite good. You can also use sets, so sets are another data structure we have access to, and it checks for membership faster. In this case, right now, these examples here were done for small lists, so it's not exactly this won't be the most performance critical for 3 or 4 indices, but if your tensors get very, very large, and you need to do this many contractions, you might need to search a couple times, so this would actually be quite worthwhile. And so you could use these sets here. And then lastly, pre-computing with a character to position map. Build a map from characters to positions up front. Oh, that's quite nice. So this is a map way of doing it, and it can do it as well. And then it gives you a nice little summary. So the index parsing overhead is typically negligible for large tensors. Exactly. For small tensors where parsing dominates, consider caching, which is basically what this last one does. So that's actually quite nice. So for our use case and our designed intended purpose, I think this is satisfactory. So thank you very much for listening and paying attention to this. If you have more questions or interest into this, absolutely leave a comment or join our Discord, and you can also join the platform and write some Aleph code yourself, and hopefully we can push this a bit further. So thank you very much for your time.